Okay, so we were studying tensors in the last class, and we'll continue doing that in this class also. So I had defined covariant, that there exist three types of tensors: covariant, contravariant, and mixed tensors. And one can uh, relate higher rank tensors to lower rank tensors by contracting indices. Of course, contraction of indices happens only if one index is upper and one index is lower. Then contraction corresponds to identifying those two indices. So in this particular example, where you have 3,1 tensor T alpha beta gamma delta, with the delta being a covariant index, if delta takes same value as gamma, then by Einstein summation convention, we would be summing gamma simultaneous at both places. And this expression has gamma summed over, and therefore only free index is alpha beta. So 3,1 tensor would be related to a 2,0 tensor by contraction. Okay, so of course it's a small exercise to check that if this T alpha beta gamma delta is a 3,1 tensor, then one can show that the T alpha beta that you obtain after contraction is a 2,0 tensor. It transforms like a tensor. Okay. Now note that this contraction rule is not commutative, in the sense that instead of contracting delta with gamma, if you had contracted delta with beta, the result would have been different. Okay, so that is the statement that T alpha beta gamma gamma is not equal to T alpha gamma beta gamma. Okay, fine. The Minkowski metric that we had defined right in the beginning, which was eta alpha beta with alpha beta downstairs indices, is a 0,2 tensor. And you can kind of check that the Minkowski metric tensor had the property that it mapped two vectors to a number. And that is this map, eta alpha beta, v alpha w beta. Okay. Of course, we haven't studied it in this way, but we know that the invariant line element, or what is called proper time, is defined as eta alpha beta dx alpha dx beta. And so if you have dx alpha dx beta defined, which has infinitesimal elements, space-time elements, then eta alpha beta will return you a number, which is what we call proper time. Okay. So the fact that it returns a number with a pair of vectors implies that it must be a second rank covariant tensor. Okay. Inverse metric, on the other hand, is a 2,0 tensor. Okay, which should have a property that if you kind of take a product of this with the metric tensor eta alpha beta, it will return you a number. Okay. Another tensor that we encounter is what is called a Kronecker Delta, and the Kronecker Delta is really a 1,1 tensor. Okay. So in reality, if you really look at Kronecker Delta, it actually implements the process of setting alpha is equal to beta, but Kronecker Delta by itself doesn't have alpha is equal to beta, and that is the reason why it's a 1,1 tensor and not a scalar quantity. Okay. Besides that, another tensor that one encounters in, say, 4 dimensions, there is an analog of that in other dimensions also. But since we are working only in 4 dimensions, we have this tensor called Levi-Civita tensor, which is a 0,4 tensor, and it has a property that alpha beta, it is totally antisymmetric in alpha beta gamma delta. And because it is totally antisymmetric, anytime alpha is equal to beta or alpha is equal to gamma, or any two indices agree, it would give you 0. Okay. The non-zero values that it would carry would be when alpha beta gamma delta would be 0, 1, 2, 3, obviously, but any even permutation of 0, 1, 2, 3. Okay. If it is an odd permutation, then it would have a value -1. Okay, so this is a kind of useful tensor when one works in 4 dimensions. Okay. So there was a small exercise again here that you can compare transformation properties of eta alpha beta, delta alpha beta, and epsilon alpha beta gamma delta under Lorentz transformations as well as under general coordinate transformation, and check that they actually have a tensor property. Okay, so what we will do is we will reserve eta alpha beta to denote Minkowski metric. Okay, just to kind of use the same notation that we have used when we are doing special relativity. And for generic space-time metric that we are going to use, we will use G alpha beta for that. Okay, so whenever we would say G alpha beta is equal to eta alpha beta, by that we would be showing that we are looking at the Minkowski metric. Okay, so eta alpha beta will always be reserved to denote excuse me, denote Minkowski metric. Okay, fine. Now, of course, G alpha beta is also a 0, 2 tensor, and the proper time defined using G alpha beta. I should have really mentioned G alpha beta as a function of X, because it's a generic space-time metric, unlike eta alpha beta, which has only constant entries. Generic space-time metric is space-time dependent. Okay, so G alpha beta, every component, that means for every value of alpha beta, is generically is a function of space-time. Okay, and the proper time is defined exactly in the same way that we had defined it in the Minkowski space, except now we replace eta alpha beta by G alpha beta, and therefore d tau squared is G alpha beta dx alpha dx beta. So if you do a coordinate transformation, say x alpha goes to x prime alpha prime, then it's kind of straightforward thing to check that dx alpha would be transformed into dx prime gamma prime through this transformation, which is del x alpha by del x prime gamma prime times dx prime gamma prime. And using this, we can ask what happens to the proper time. And the proper time would be written as G alpha beta, and dx alpha and dx beta would be replaced by using this rule, and that would give us G alpha beta times del x alpha by del x prime gamma prime times del x beta by del x prime delta prime times dx prime gamma prime dx prime delta prime. Okay, so looking at this expression for the proper time up here, we can easily read out that the term on the right hand side of the d tau squared written here contains dx prime gamma prime times dx prime delta prime. So whatever object that you have here, you could identify that as a metric in the x prime coordinate system, and therefore we would call it G gamma prime delta prime. Okay, I should have really called it G prime gamma prime delta prime because it is a different function of different coordinates. Okay, so I'm being a bit sloppy here. I'll correct it next time. Okay, so it would be a different function of different coordinates, which could be labeled by different variables. Okay, so for example, this could have alpha beta, or coordinates could be just Cartesian, whereas gamma prime delta prime coordinates could be quite complicated system, which would which would be maybe a spherical coordinate system or maybe infalling coordinate system, all kinds of stuff. Okay, so therefore that is the reason why primes on various things, just to be able to distinguish them. Okay, fine. So what we learn by doing this transformation is that the proper time would have the same form in the prime coordinate system after doing the coordinate transformation. Okay, but that also tells you that the metric in the prime coordinates is related to the metric in unprimed coordinates through this transformation. Okay, because G alpha beta dx alpha by dx prime gamma prime times dx beta by del x beta by del x prime delta prime is the expression for G gamma prime delta prime. Okay, so this is how the new metric would look like. But this is precisely the transformation of a 0, 2 tensor, right? And in that sense, we know that G alpha beta would transform as a 0, 2 tensor under a coordinate transformation. We can kind of explicitly see that. Okay, fine. So you could ask the question, what happens if you look at the inverse metric G alpha beta with upstairs indices, contravariant indices? Okay. So what you can do is you can show that G gamma prime delta prime is equal to G contravariant indices alpha beta times del x prime gamma prime by del x alpha, del x prime delta prime by del x beta under a general coordinate transformation, which takes you from x alpha coordinate system to x prime alpha prime coordinate system. Okay, there are multiple ways of showing this. You could kind of follow the method that we have used here. You can, I mean, there are 2-3 ways of doing it. You may want to try more than one way of showing this relation. Okay, so like the Minkowski metric, the metric on general space-time, general curved space-time, also can be used for raising and lowering indices on the components of any given tensor. Okay, so for example, if you have a tensor with 2 contravariant indices and 2 covariant indices, you could use an inverse metric G gamma sigma to pull one of this index up, okay, and write down a tensor with 3 contravariant indices and 1 covariant index. Okay. Similarly, you can use the metric to convert a contravariant vector to a covariant vector. Okay. So this transformation you can carry out for any tensor which has at least one index. Okay. So for example, G alpha beta would not do anything to a scalar. Okay, if you multiply G alpha beta to a scalar, you get a quantity which is a scalar times the metric. It would of course look like a second rank tensor, okay, but it is not actually transforming anything into anything else. Okay, that transformation is very similar to what we had said earlier about how the tensors kind of be used as maps from one vector space to another vector space. So let me just step back here. And we said that if you have a tensor like this, it would map a contravariant tensor to a contravariant tensor. But you can easily imagine that instead of having 1, 1 tensor, if you had a 0, 2 tensor, that means a tensor with both covariant indices, then it would take a contravariant vector to a covariant vector. Okay, which is what was the G alpha beta taking a contravariant vector to covariant vector that we had written down. But you could also have a contravariant, you could also have a tensor with 2 covariant indices acting on a scalar, and it would give you a covariant second rank tensor multiplied by that scalar, obviously. Okay, so you can think of tensors being maps from one tensorial space to another tensorial space, where tensors in general would be defined as scalars, vectors, second rank tensor, third rank tensor, depending upon how many indices it carries. Okay, so that allows us to unify this language and call everything a tensor as long as it transforms homogeneously under coordinate transformation. Okay, so if the object does not carry index, it would not transform under coordinate transformation, and we would call it a scalar. Okay. So in this sense, this transformation is consistent with the way we had defined how the tensors would transform vectors to vectors. In this particular case, what we are doing is a tensor is transforming a vector to a dual vector. Okay. Fine. So now, given that generic tensors have multiple indices, when I say this, I am of course excluding scalars and vectors, because scalars don't carry any index and vectors carry only one index. But barring that, any higher rank tensors carry multiple indices, and then those, with respect to those indices, tensors may have some symmetry property. Okay, for example, a tensor which is symmetric under some of its indices, okay, would not change if you exchange those indices. For example, if you have a T alpha beta gamma delta, which is a 0, 4 tensor, okay, with 4 covariant indices, if this fellow is symmetric in first 2 indices, say alpha beta, then if you swap alpha and beta, the tensor would be same. Okay, so therefore T alpha beta gamma delta would be same as T beta alpha gamma delta. Okay, so of course, if that is the case, then you can easily imagine that the total number of independent components that the tensor would have would be reduced, because earlier T alpha beta gamma delta was different from T beta alpha gamma delta. But now, if the tensor has a symmetry property under exchange of alpha beta, then those two elements are identified. So whenever you have exchanged first two indices in this particular example, you would have the same value for the tensor component. Okay. Now clearly, if you have a tensor carrying multiple indices and if it is symmetric under only say two indices, in this example alpha and beta, then there is no statement that we will make about remaining indices. For example, there is no statement that we can make about what happens to a set involving alpha gamma delta or beta gamma delta. Okay, there is nothing that we can state that they are symmetric or they are anti-symmetric. Nothing. Okay, because we have not stated any symmetry property with respect to those indices. Okay, so if you have a tensor carrying multiple indices and it has a symmetry property with under the exchange with respect to say one pair of indices, then all other indices and any one of this pair, okay, may not have any symmetry property, which is generally true now. Okay, unless of course there is additional symmetry. Okay, so we will see tensors which should have this kind of transformation properties, and those transformation properties would be useful for us to kind of restrict the total number of independent components that the tensor would have. Okay, fine. So besides having the symmetric tensor, we could also have an anti-symmetric tensor, and a tensor would be called anti-symmetric under the exchange of some of its indices if it's flip side. Okay, so suppose we have a tensor A alpha beta gamma delta. Okay, and if it goes to minus A beta alpha gamma delta, then we would say that A alpha beta gamma delta is anti-symmetric with respect to exchange of alpha and beta. Okay, so like in the symmetric case, here also we cannot make any other statement involving the complement sets, namely alpha gamma delta and beta gamma delta. Okay, within this set we have no definition of, we have not defined any symmetry or anti-symmetry property, and therefore any combinations of values of these indices, the tensor generically has some non-zero component. Okay, and there is no symmetry relation between them. Fine. Now the question that I would like to ask, given this fact that we can use metric and inverse metric to raise and lower indices, okay, then you can multiply. For example, you look at this expression and you could say that, like, okay, I pulled one covariant index upstairs and wrote down a new tensor which has 3 contravariant and 1 covariant index. Okay, so I could multiply by one more G inverse. For example, I write down G, say rho delta, and I can pull that index up also and write down a T alpha beta gamma rho with all indices contravariant, all indices upstairs. Okay, so given the fact that metric and inverse metric allows me to raise and lower indices freely, a natural question would be, why do we distinguish tensors as covariant, contravariant, and mixed when we can shuffle them by just using the metric and its inverse? Okay, and there are of course several reasons for not doing that, and they are all basically related to the ease of doing computations in some sense. Okay, so first of all, generic metric G alpha beta that we would write down is quite complicated, is expected to be quite complicated. Of course, you can have examples in which G alpha beta would be simple. For example, say Minkowski space or many other spaces in which you have a lot of symmetry. G alpha beta may look like a simple metric, and in that case, of course, you may be lucky. Okay, but a generic metric would be quite complicated, and as a result, if V alpha, a vector with contravariant index, if that expression is a simple expression, V alpha, which is a covariant vector, may have a very complicated form simply because the metric is very complicated. Okay, so by knowing the values of the components here, it may not give you any clue as to how this components would look like, okay, or whether these components would be easier to deal with, okay. Now, of course, if you know the metric, you would eventually know how these components would look like, but they may not be very easy to manipulate. It may be much easier to kind of continue working with contravariant index object, uh, like a vector, than with the dual vector, okay. Fine. Now, second thing is that, like, you may have a tensor which has one index upstairs, one index downstairs, and but if you try to pull that index, if you try to have both the indices downstairs or upstairs, doesn't matter, okay, then you may be able to define symmetry or anti-symmetry property of the tensor, okay. But that property you cannot define when the index, say, one index is covariant and one index is contravariant. Okay, so therefore, sometimes it may be useful for you to write down the object with purely covariant indices or purely contravariant indices and check what kind of symmetry property that tensor has. Okay, but eventually the tensor with mixed symmetry may be more relevant. Yes, yes, please. Hello, hello.
Yeah, so
Sorry, there was a question, I thought. Hello.
I think you should carry on.
Oh, okay, okay. So there was, I thought there was a question. Sorry. Okay, so let's continue. Okay, so the second reason is actually, you may have to shuffle the indices up or down to just study the symmetry, but the mixed tensor may be a more useful object to work with, in spite of knowing the fact that it may have certain symmetry or anti-symmetry property when it is purely covariant or purely contravariant. Okay. The third thing is that the gradient and operator and its action on a vector is defined without any reference to a metric. Okay, so remember, gradient is I don't know whether I defined this. Can I just try going back a little? Okay, I guess maybe I can just I thought I had defined it somewhere. Yeah, here. Okay, so here's the gradient operator, and so in this particular case we are looking at the gradient of a scalar, but if you are looking at a gradient of a vector, then you can just replace phi by a v, and v would have given you say v beta e hat beta, and then theta alpha with e beta would have given you a delta alpha beta relation and it would give you a gradient of a vector, okay, would have been defined without using any metric. Okay, it is purely a inner product between the basis and dual basis expressions, and therefore you would write down this expression without using any notion of metric on the space-time. Okay, now that shouldn't surprise you, because our entire definition of vectors and tensor didn't really care about defining any notion on of distance on space-time. Okay, but of course, if you define a notion of distance, it is going to be useful, which is what we said, that we can define a metric to raise and lower indices on the tensors. But if you didn't have a metric, you could still have studied tensor algebra and tensor calculus. Okay. Okay. So yeah, we have. Okay. But if you want to do the same thing, instead of using the gradient, which is like a derivative with covariant indices, if you try to do it with contravariant indices, index, then you will definitely need a metric. Okay, so in that sense, randomly kind of writing down quantities by raising or lowering indices would of course necessarily require intervention of a metric. Okay, so in that sense, it would be much more easy to kind of work with, say, a mixed tensor or purely covariant tensor than try to kind of shuffle indices of it. Okay, so here's another small exercise. So here's a mixed tensor r beta gamma, and we are taking a derivative of that, and so del x alpha of r beta gamma gives you this new quantity, which is t alpha beta gamma. Okay, now if r beta gamma transforms like a 1,1 tensor, okay, that is of course given. Okay, then you can check how t alpha beta gamma would transform under the coordinate transformations of this kind. Okay, so this transformation property we have already written down, not for r but some t alpha beta kind of mixed tensor. So use that property, use that property and try to find out how t alpha beta gamma would transform. Okay, it's a small exercise, but it is instructive. In fact, it will be useful in the lecture today itself. But yeah, but you could kind of try to compute it at some point. Okay, so if you have two tensors of the same rank and if they are equal in, say, any choice of basis, then they would be equal in any other basis. Okay, so that is one good property because of, and this is guaranteed because of the homogeneous transformation properties of tensors, that if they are same in one coordinate system or in one choice of basis, then they would be same in all other choices of basis. Okay, so therefore you don't have to redo this computation by changing coordinate systems. Okay, if you have shown them to be equal in one, you have done the job for all coordinate systems. Okay, so in that sense, work is kind of simpler. Okay, it's reduced. Okay, so let's now talk about the equivalence principle. So let's start with the Newtonian mechanics. Okay, so maybe before that, any questions about these tensors, vectors and tensors? Okay, maybe if there are no questions, then I'll go ahead and talk about the equivalence principle. So as I said, we will start with the Newtonian mechanics. In Newtonian mechanics, Newton's second law states that the acceleration that a body experiences, that acceleration is proportional to the force exerted on the body. Okay, this is kind of a elementary stuff for all of us. Okay, and the law says that the constant of proportionality in this particular relation is what is called the inertial mass of the body. Okay, so therefore we would write that equation as vector F is equal to mi times a, where mi is the inertial mass of the body. Okay, so this is a part of Newton's second law. Okay, and this is just a proportionality constant. Okay, similarly, if you study, say, non-relativistic problem with gravity, okay, then the gravitational acceleration is also proportional to the force exerted by on a body by a gravitational field. That gravitational field could be produced by another massive body. Okay, so for example, sun could produce gravitational field, and planets could go around, and Earth could produce gravitational field for, say, moon to go around or humans to jump around and stuff like that. Okay, so in that case, we have a proportionality constant again, which tells you how the gravitational force generated by the gravitational field is related to the gravitational acceleration. and that quantity is written as the what is called the gravitational mass. Okay, so we write down F is equal to mg times the gravitational acceleration g. Okay, and the gravitational acceleration is written in terms of the gravitational potential as minus the gradient of phi g. Okay, so this expression that we have written down is quite akin to the situation in electrodynamics, where the force exerted on the charged particle is proportional to the applied electric field. Okay, and the constant of proportionality in that case is what we call the electric charge. Okay, so here's the equation that F electromagnetic is Q times the electric field. Okay, and electric field is of course minus the gradient of the Coulomb potential, which is what I call phi E. Okay, so by this analogy, you could think of mg as as gravitational charge of the system. Okay, uh, whereas g itself is producing gravitational field in some sense. Okay, fine. So in some sense, these two phenomena, one corresponding to uh, the Newtonian mechanics, which involves uh, acceleration generated due to force, uh, has no connection with the problem of gravity, which is a gravitational acceleration generated by gravitational field. Okay, and therefore these two constants of proportionality in principle could have been different objects. Okay, but nevertheless, Galilean uh, equivalence principle, which is also called the weak equivalence principle, states that the inertial mass is same as the gravitational mass. Okay, okay, so that is that famous uh, experiment by Galileo, which he probably never did, in fact. But nevertheless, that experiment which says that all bodies, irrespective of their composition, would fall at the same rate. Okay, uh, fine. So there are several implications of the weak equivalence principle. So we'll just look at them right now. So first thing is that the motion of a body in the gravitational field does not depend on the composition of the body. So this is what was Galileo's statement, uh, and uh, and of course, a lot of experiments were done later. Although Galileo himself did not do any experiment with respect to leaning tower of Pisa at all. Okay, but people seems to state that to be the check that he did with his proposal. Uh, I think he believed his theory much better and didn't require any experiment to actually prove it. Okay. Uh, Although I'm not proposing that that's what you should believe all the time. Okay. I mean, except you want to do string theory. In that case, of course, you are allowed to do anything. Okay. So, coming back to the implications of equivalence principle, uh, first thing, as I said, it is independent of composition of the body. Okay. Second thing is that the local effects of gravitational field is indistinguishable from the effect experienced by an accelerated observer in a flat space time. Okay. So in other words, gravitational acceleration and any other acceleration are essentially same objects. Okay, that is the claim. Okay, so that is one of the reasons why the constant of proportionality in say Newton's law involving acceleration is same as the constant of proportionality that a gravitational law would involve. Okay, so that is the statement. So locally, both these effects are identical. Okay, it also in some sense implies that the freely falling body would not experience any force. Okay, and that is simply because a freely falling body is essentially yielding to the force generated by gravitational field and falling at a rate at which the acceleration would have asked it to fall. Okay, so the sense of weightlessness that freely falling object would feel is a statement of it not experiencing any force. Okay.
Sir,
Yes.
so how does the second point follow from that mi equal to mg? That local effects are indistinguishable?
Oh, that is because if any acceleration had, say, if you look at Newton's law, second law, then it would say that any accelerating frame uh, ex- would see an object feeling a force, okay, and the constant of proportionality is mi, which is the inertial mass, okay, right?
Yes.
Okay. Now, if you are looking at gravitational field generating acceleration, okay, then this equivalence principle would say that the gravitational field would generate the same kind of acceleration. Okay. So the inertial mass being equal to gravitational mass would mean that if you accelerate a system by applying a different kind of force versus if you accelerate a system by applying gravitational force, you may not be able to distinguish between them. Okay.
So
If
by
the
local effects, you mean just those accelerations and all those things?
yeah, local accelerations only. Yeah.
Okay.
Yeah. Okay. Fine. So suppose you have an observer who is sitting outside, okay, and watching a freely falling object, which is what we would call a freely falling reference frame. Then from the observer sitting outside, like somebody sitting on the on Earth and uh, seeing some uh, projectile fall, for example, or something which has thrown up, come down, this thing, that object would look like an uh, accelerating frame, and the acceleration that that frame has with respect to the outside observer is precisely equal to the acceleration due to gravity. Okay, so therefore, according to weak equivalence principle, that acceleration is related to the gradient of the gravitational potential. Okay, and it does not care about how this is how the body is composed. Okay, okay? So in that sense, the mass of the body is irrelevant in determining what is the gravitational acceleration. Okay, so therefore weak equivalence principle can also be stated in the following way, that in a small enough region of space-time, laws of physics in a freely falling reference frame are identical to those in a gravitational field or those in an uniformly accelerating frame. Okay, so we have already stated that if you have a gravitational field, the reason why one is talking about small enough region is because uh, because of the following reason, that one is trying to assume a uniformly accelerating frame being related to the acceleration generated by gravitational field. Now you may have a gravitational field having a different gradient, and therefore not only that the acceleration, but uh, the acceleration itself could change. For example, gravitational acceleration is 9.8 meters per second squared, very close to the surface of Earth. If you start going up, then this number itself changes. So acceleration itself has its own gradient. Okay. So therefore, to avoid any confusion between this gradient and anything that would happen in an accelerating frame, in which you would naturally assume the acceleration to be constant, if you choose a small enough region, then the gravitational field wouldn't change. For example, if you try to look at a uh, system which is, say, on Earth versus 10 feet above the Earth. Okay, in this much region, the gravitational potential wouldn't change much. Okay, and therefore you should be able to kind of see the effect due to gravitational field and compare that with a uniformly accelerating frame. Okay, now of course technology has reached a level where even within 10 feet you should be able to kind of distinguish these effects, but let's assume that we are not doing that an accurate experiment. The reason why I'm saying this is because um, to measure something called a redshift effect, uh, an experiment was performed in Harvard lab, which was where some light was shown from 20 feet above the surface of Earth and collected on the surface of Earth, and just that measurement of about 20 feet height was done using Mossbauer effect, and actually checked that was the first detection of redshift due to gravitational field. Okay, so the real change in acceleration due to gravity within 20 feet is really minute, but Mossbauer effect can actually pick up even that smaller change, and um, therefore purely can theoretically you wouldn't want to kind of go to large distances, but in small enough region this statement would still be valid. Okay. Okay, so now let's go to Einstein's equivalence principle. And so maybe any questions about this first, the weak equivalence principle? Okay, maybe not. Okay, so let's go over to Einstein's equivalence principle. And Einstein's equivalence principle states the following thing, that in a small enough region of space-time, laws of physics reduce to those of special theory of relativity. Okay, so a small change from the weak equivalence principle, that you are talking about special theory of relativity in this case, which also implies that in the small enough region, given that you are talking about special theory of relativity, there is no effect due to gravity. Okay, so therefore it is impossible to detect any effect due to gravitational field locally. By locally, I mean in small enough region. Okay. Now remember that in special theory of relativity, we did not talk about various things. Okay, various things were kind of not part of special theory of relativity discussion. One of them was gravity itself. Second uh, thing was like very little discussion about accelerations, for example. Okay, most of the discussion was concentrated on talking about inertial frames. Okay, so inertial frames play a very important role in uh, special theory of relativity. And let's define the inertial frames in the following way, that among all kinds of reference frames that you could define, uh, we will isolate a subset of frames and we'll call them inertial frames with respect to all other frames within that subset. Okay, so what we are doing is we are looking at a set of all possible reference frames. Okay, now within that set, of course, you can find a subset where all the frames within that subset are inertial with respect to each other. Okay, then you may have another subset, all frames within that frame within that subset are inertial with respect to each other, but this set uh, may not be inertial with respect to the second set. Okay, so set 1 or set A and set B themselves may form collection of inertial frames with respect to each other, but any frame in set A may be accelerated with respect to any frame in set B. Okay, so we categorize, or we kind of compartmentalize all reference frames into equivalence classes of mutually inertial frames. Okay, and different equivalence classes are accelerated with respect to each other. Okay, so if you define an inertial frame in this fashion, then the concept of acceleration is uniquely defined with respect to this set of inertial frames, because that is the one which will, the acceleration will take you out of this set and relate one uh, subset of inertial frames with another subset of inertial frames. Okay, so the equivalence principle implies that the
Sir, how are you defining inertial frame here?
how am I defining inertial frame?
Yes.
Exactly in the same way that we defined in special relativity. That means the two frames are related to each other by constant velocity, or they may be related to each other by rotation. Okay,
Right.
constant
So,
velocity is equivalent to Lorentz boost.
Yeah, but that definition only defines relation between inertial frames, right?
That is
So
right.
in order to define one inertial, if you find the one inertial frame,
Yeah.
then using that definition we can find another inertial frames,
Yeah.
right?
So, I mean, there is nothing called one inertial frame. You choose one frame, and with
Yes.
respect to that frame, you define all possible inertial frames by doing Lorentz transformations,
Okay.
right?
But
So, yeah.
for inertial for defining inertial frames, we define inertial frame to be a frame in which if we leave one particle without a force, it go travels in a constant velocity or stays at rest, right?
Yes. Yes.
So will that definition hold here?
Yes, certainly, because all other frames, suppose a particle is at rest in one particular frame, then all other frames in a subset in which there are frames which are related to this frame uh, by Lorentz transformation would see this particle moving only with uniform velocity,
Right.
right?
So that so in presence of gravity also that definition will hold.
No. So in presence of gravity, of course, we are going to only define local inertial frames. Okay.
Okay.
So the two uh, that is one of the reasons why we also wanted to define tangent spaces locally. Okay. So we will define only local inertial frames, and when the particle moves from one location to another location, there is another local inertial frame, and we want to give a relation between local inertial frame at point P and a local inertial frame at point, say, P plus delta P. Okay,
Okay.
that is what we would like to do, and that is the one which will incorporate information about gravity.
So the classes of inertial frames that you just mentioned,
Yeah.
those classes will lie at different points.
No, no, no. They could lie at the same point also, right?
Okay.
Because at any given point, you may have frames which are kind of uh, related to each other by constant velocities, or could be related to each other by constant acceleration, for example, or
Okay.
even non-constant acceleration. Okay.
Okay.
So you define these quantities locally, okay, and then you want to relate them at different points. That is the relation that we will start developing soon.
Okay. Okay.
Okay. Okay. So Einstein's equivalence principle implies that gravity interacts universally. Okay. And that is because of the fact that, like, in a local frame, it is always possible for you to kind of nullify the gravity effect. Okay. So now it interacts universally in a yet another way, and that is that there is no object which is gravitational neutral body. Okay, so compare this with electrodynamics. In electrodynamics, you have a positively charged particles, negatively charged particles, and neutral particles. So you can define charges with respect to this neutral object, and of course, you still have an ambiguity of what you call positive versus what you call negative, but you can definitely say that this body is charged versus this body is neutral by just checking how the electric field impacts, say, a motion of a particular object. So if a particle is neutral, electric field would not accelerate or bend its path, whereas um, if it is charged, it would. Okay, or magnetic field would bend the path or something. Okay, so uh, compared to that, in gravitation there is nothing called a neutral body. There is no object which does not gravitate. Okay, because if it was that kind of object, then with respect to that object we could have defined a notion of acceleration due to gravity. Okay, so therefore acceleration due to gravity is not an absolute definition, because there is no gravitationally neutral body, but acceleration due to gravity in some sense is a relative notion. Okay, it depends upon in which frame you are. You, in some frame you may not see acceleration, you in some frame you would see the acceleration. Okay, fine, good. So as I said, that therefore this principle also implies that acceleration due to gravity is a frame dependent quantity. Okay, and what we will do is that we will choose to define an observer unaccelerated if the observer is freely falling. Okay, so let's try to understand this freely falling observer statement. Now imagine, you have some object, say at 10 feet distance above the surface of Earth. Okay, so if it's 10 feet above the surface of the Earth, then you clearly know that if you want to keep that object 10 feet above, you'll have to continuously apply some force for it to stay there. Okay, is that right? So either you have to hold it by a hand, or you have to have some, thruster which will kind of continuously apply a force so that the object is there. So in that sense, an object which is held fixed at a distance 10 feet above the surface is an accelerated object, because it has to have a force acting on it to stay in its own place. Okay. On the other hand, if you let that object be as it is, it would just fall straight down to the ground, and the rate at which it will fall is determined by the gravitational acceleration. That fall is free fall, and it is not experiencing any force. And the reason is exactly what's the statement of the equivalence principle, that in a small enough region, you would not see the effect due to gravity. Okay, and if you do not see the effect due to gravity, then the freely falling object that you see, okay, is experiencing no force. Okay, fine. So therefore, we may want to use a language where we could say that an unaccelerated observer is a freely falling observer. Okay, fine. So let us try to define a notion of an unaccelerated observer in a little more concrete way. And so for that, let us go over to something called the geodesic equation. Okay, so we'll kind of hopefully discuss it today. So let us consider an unaccelerated observer O in a frame denoted by x alpha. Okay, so within this frame, this observer is what you would call an inertial observer. Okay, since it's an inertial observer, it will be moving with a uniform velocity in the frame x alpha. Okay, now remember, in an arbitrary frame, it would be accelerating, but within this definition that you have a frame x alpha and O is an unaccelerated observer in the frame x alpha, would mean that it would be moving with uniform velocity. Okay, and for uniform velocity, you would typically have a straight line space-time trajectory. This is something we know from special theory of relativity. Okay, and the equation of motion for an object or of this kind, which is undergoing a uniform velocity, is like this. It is d2x alpha by d lambda squared is equal to 0, where lambda is parameterizing the world line trajectory of the object, of the observer. Okay, and setting this second derivative to 0 basically is a statement that the observer is not accelerating. Okay, so that is the equation that we write down. It is no big deal. We have done this in classical mechanics also several times, that mx double dot is equal to 0 is a free particle equation of motion. That is the kind of equation that we are writing down. Only thing is, instead of using time, we are using parametric description of the space-time trajectory of the observer or the particle that we are looking at. This equation can be solved trivially, and this is the most general solution. X alpha is equal to V alpha lambda plus X naught alpha. Okay, where this is just the initial position, and V alpha is the velocity, which is of course constant. Okay, it's a uniform velocity. So this is the most general solution that you can write down to this equation. Okay, so what we want to do is that we want to consider a new frame, which we call x prime alpha prime, which is related to x alpha by a general coordinate transformation. Okay, now remember, when I say general coordinate transformation, I mean that it is a map from x alpha variables to x prime alpha prime variables, which is an arbitrary function. Okay, only condition that we are going to impose on that arbitrary function is that this map is invertible. Okay, fine. And the reason why we want this map to be invertible is because Otherwise, the notion of distance defined in one space may not be related to the notion of distance defined in another space. Okay, you can make quantities which are kind of finite distance away in one coordinate system to be equal to infinite distance away in another coordinate system by doing non-invertible maps, okay, transformations. But that is of no interest to us because it physically makes not much sense to consider transformations of those kind. Okay, so only condition that we are putting on general coordinate transformation is that it's an arbitrary function of x alpha. X prime alpha is written as arbitrary function of x alpha, which is invertible. That's all. Okay, good. So if you do that transformation, we want to look at what happens to this equation. Okay, fine. So let's check. Okay, so we are going to convert from x alpha to x prime alpha, alpha prime. So use the chain rule, d by d lambda acting on dx alpha by dx prime beta prime times dx prime beta prime by d lambda. Okay, so this is a chain rule that we are imposing on the first derivative. Okay, so I'm taking one derivative outside and write dx alpha by d lambda and using a chain rule there. Okay, and of course d by d lambda I will have to act on this entire stuff, but at least this is a chain rule that I have used. Now let's apply d by d lambda on this. Okay, so d by d lambda would act on both these quantities. When it kind of does not act on this and acts on dx prime by d lambda piece, then you get this term. Okay, where dx alpha by dx prime beta prime just sits around, and you have second derivative with respect to lambda piece. Okay, which is very analogous to what we have here. Okay, albeit it's multiplied by some factor, but it's very similar to that. Okay, the other case is when d by d lambda acts on this quantity. In that case, you have a first derivative piece sitting around and d by d lambda acts on this. Okay, what you do is, in this case, is again use the same kind of chain rule that we used, that you define a second derivative of this object with respect to gamma and write dx prime gamma prime by d lambda. Okay, that is just using a chain rule of d by d lambda acting on this particular piece. Okay, now since this entire expression is just d squared x alpha by d lambda square, this whole expression better be 0, because that is what the equation of motion was. Okay, so right hand side continues to be 0 even after you do the coordinate transformation. Okay, fine. So what we'll do is we'll multiply just to kind of bring this equation into the form where this second derivative with respect to lambda of the coordinate has coefficient 1. Okay, what to do that, what we'll do is we'll multiply this entire equation by dx prime alpha prime by dx alpha. Okay, if you do that, then you can use chain rule again and write down dx prime alpha prime by dx prime beta prime, which just gives you delta alpha prime beta prime. Okay, and then you replace beta prime by alpha prime everywhere. Okay. Okay, so if you do that, then you get this expression to be dx prime d squared x prime by d squared x prime alpha prime by d lambda squared plus this entire piece multiplied by dx prime alpha prime by dx alpha. Okay, so that is how this equation is going to look like. Okay, agreed? Are you with me on this manipulation?
Yes.
Okay. Okay, so we get an equation which looks like this, and first thing that we notice is that the equation that we had written down earlier, which is second derivative of x alpha with respect to lambda is equal to 0, is not form invariant at all. Okay, under general coordinate transformation. Okay, we of course know that this equation is form invariant under Lorentz transformation. Okay, this statement was Lorentz invariant statement. Okay, and therefore we started off with this, but instead of doing Lorentz transformation, what we are doing is general coordinate transformation. And if you do a general coordinate transformation, then we find that that equation which was Lorentz invariant in the special relativistic setup is not form invariant at all. Okay, and I changed to this form. Okay, so what do we learn from this? Okay, so let's do the following thing. Okay, let's define a new quantity which we will call gamma alpha prime beta prime gamma prime, okay, to be whatever this piece sitting around here. Okay, so remember, first piece is equal to 0 would have been the equation that that was original coordinate system equation, and we would have been happier to have it in that form. Now that we have found that it is not of that form, we try to understand what is happening to the entire equation. So we will try to interpret this piece, okay, and we try to call this expression to be gamma alpha prime beta prime gamma prime. Okay, notice here that in this expression, or maybe since it is written down again here, in this expression, alpha is summed over, it is contracted. Remember, Einstein convention tells you that if the indices are repeated, they are summed. Okay, so alpha is not a free index. Only free indices are alpha prime, beta prime, and gamma prime. Okay, which is precisely the set of indices this object capital gamma is carrying. Okay, so if you define this quantity to be capital gamma, then this equation, you replace this by capital gamma, and this equation takes the form d squared x prime alpha prime by d lambda square plus gamma alpha prime beta prime gamma prime times, okay, I mean it's the same stuff, so we can just read it off here, times dx prime beta prime by d lambda dx prime gamma prime by d lambda is equal to 0. Okay, so as I said, that original free particle equation is not form invariant under general coordinate transformation, but what we will see is that this equation, okay, we would like to know whether this equation would be form invariant if I do a general coordinate transformation. Okay, fine. So what we are going to see now is that we will treat this equation, which is numbered as equation 4. Okay, we will ask whether what happens to this equation if I do a general coordinate transformation. Okay, fine. So just to understand that, we can look at this equation again, replace all these primed variables and primed coordinates by unprimed variables and unprimed coordinates. Okay, that would be our starting point. Okay, and consider a coordinate transformation from unprimed variable to prime variable again. Okay, so from now on, I'm just going to use GCT to describe general coordinate transformations. Okay, I hope that is okay with you. It just takes too much time to type general coordinate transformations. I'm sorry for that. Okay, so let us consider a general coordinate transformation x alpha to x prime alpha prime. Okay, and replace all these primed variables by unprimed variables and see what happens to this equation. Okay, so I'm repeating that computation again. This is something that we had seen just a couple of slides ago, that the second derivative piece d squared x alpha by d lambda squared would be written in this particular form. Okay, what we'll do is we'll take this expression and put it back in this equation without having primes on them. Okay, so I'm trying to save on writing this equation again, but think of this equation without any primes anywhere. Okay, and take that equation and substitute this piece in the place of double derivative with respect to lambda. Okay, that would give you an expression which looks like this. Okay, so the first two terms are the terms which are sitting around here. Okay, sorry, I should have had a dx prime gamma also piece here. Okay, disaster, I should correct that. Okay, just hold on. Okay. So, so you get an expression like this. Okay. And it is still correcting. Yeah. Okay. So, so this is what you should get. I'm just copying this from here to here. Okay. And gamma, alpha, beta, gamma, I keep as it is, and just use the chain rule to write down dx beta by dx by d lambda and dx gamma by d lambda in terms of dx prime beta prime and dx prime gamma prime. So that this is a chain rule expression. Okay. That is what would happen. Okay. Now what we want to do is that if we want this entire expression to be form invariant, that means it looks exactly same as this expression. Okay. Except, you know, either you have primes replaced by unprimes or unprimes replaced by prime. Okay. But expression is the same. If you want it in that fashion, then that would happen by defining how gamma would transform. Okay. So to do that, again, we would like to get this second derivative piece with coefficient 1. So you again multiply by dx prime alpha prime by dx alpha to entire expression. Use chain rule here to convert that into delta alpha prime beta prime. Okay. And that gives you an expression which looks like this. Okay. So notice that the dx prime, dx alpha by dx prime beta prime has been removed by this fellow from the first expression, and dx prime alpha prime by dx, I mean I'm using d, but I mean del x prime alpha prime by del x alpha is appearing in all other terms. For example, it is appearing here in the second piece and it's appearing here in the third piece. Okay, fine. We want to claim that this expression of its first part looks the same as the first term in the other equation. Okay, so let me see if I can do a small trick to kind of see that equation simultaneously. Okay, so here, can you see the second screen below?
Yeah.
Yes, we can.
Okay, so this is the equation that we were looking at, and this is the transformation of that equation. There's a small issue, but I had mentioned it, that we start with the equation without primes, and that goes into this equation. Okay, and we want this equation to look exactly like this equation. So of course the first piece is same, so that part of the problem is solved. The remaining piece, notice, has uh, terms like dx prime beta prime by d lambda, dx prime gamma prime by d lambda common. So you can pull that out and collect the remaining part of the expression. Okay, and that is the following. So that tells you that if you say that a new gamma alpha prime beta prime gamma prime is written as these four pieces, gamma plus these three partial derivatives plus this second derivative piece times this partial derivative. If you say this, that new gamma prime is related to the old gamma, okay, through this relation, then our equation would look exactly same as this one. Okay, we would recover this equation. You see that point? That just pick up this part. Okay, so let me see if I can do. Okay, so. Oh, disaster. Okay, I think next time I'll think a little before I kind of play around with these things. Okay, it doesn't matter. So these two pieces, if you collect, then your equation is taking the same form as the original one. Okay. So the point that we are going to conclude out of this is that if you write down your equation as equation 4, okay, and allow this object gamma, which was initially defined only through this transformation, because what we did was we took a free particle in Minkowski space and did an arbitrary coordinate transformation, and we landed up with this object. we just defined that object to write down this equation. And then we elevated that object. By elevated, I mean that we basically freed this object from this definition. And we just said that like this object exists as it is. It would transform under general coordinate transformation. How it will transform under general coordinate transformation will be figured out by actually doing a general coordinate transformation, which is what we did here. We just started off with that equation and did arbitrary general coordinate transformation. We got some mess like this. We kind of cleaned it up a bit by multiplying by appropriate stuff, made it look like that. And then looking at this expression, we realized that if gamma had transformed in this fashion, then this equation would have maintained its form. Okay, that is what we want. We have a form invariant equation now in arbitrary coordinate system. Okay, and this equation is called the geodesic equation. Okay, now one of the reasons why it is called a geodesic equation is because geodesic is the one which follows the so-called shortest path. Okay, and it is guaranteed for us that this will follow the shortest path because in the original coordinate system it was following a straight line path. Okay, between any 2 point, a straight line path would be shortest if this metric was flat. Okay, you change the metric to a complicated metric, the corresponding equation would change to complicated equation, but the path would remain the same. Okay, it may not look like a straight line path simply because the metric is complicated, but the fact that it is a shortest path is that fact continues to hold. Okay, so geodesic equation therefore is a statement that in a locally inertial frame, the path of the particle or the observer which is following the geodesic would be a straight line locally. Okay, fine. Any questions here? Okay, maybe if there are no questions, let me say one important thing that we have just noticed or just obtained, and that is that we had said that any object which carries more than one space-time index, we would call it a tensor. Okay, well, anything which carries one in space-time index also is a tensor, but we have a special word for that. We call it a vector, covariant or contravariant. But if it carries two indices or higher, we typically call it a tensor. Okay, and we were careful in defining tensors because we said that like an object which carries multiple space-time indices and transforms homogeneously under coordinate transformation is called a tensor. Okay, and here is an expression which is the first time that we encounter an object which carries space-time indices, in this case alpha prime, beta prime, gamma prime, but under coordinate transformation it does not transform homogeneously. Okay, by homogeneous transformation I mean that gamma is related to gamma and nothing else. Okay, in this case the transformation is not like that. In this case gamma is related to some partial derivatives times gamma. The number of partial derivatives is exactly the number of indices it has. And the index structure on the partial derivative is exactly the way the indices are sitting around. Alpha prime is upstairs, beta prime and gamma prime are downstairs. Similarly, here, alpha is upstairs, and that's why it contracts correctly, and beta and gamma contracts correctly. Okay. But in addition to that, you have this piece sitting around here, and this is nothing like any tensor would transform. Okay, so this is the first time we are seeing an object which has multiple space-time indices but is not a tensor. Okay, so this gamma is an object which is called a non-tensor. Okay, and it's exactly the way I said that the tensors are very useful in defining certain invariant quantities, some things like conservation laws and stuff like that, which are or certain laws which are true in every frame. Then it is best to state them in a tensorial language, because then if you show that that law is true in one coordinate frame, then that law would be true in all coordinate frames which are related by general coordinate transformation. Okay. Now, so that is the advantage of having tensors. Okay. But here is a object which is not a tensor, and we will see what is the advantage of having this object also. For example, if you are, I mean, in some sense, we are going to go backwards in whatever we did just now, okay, in today's class. But you can imagine that you have gamma non-zero in some coordinate system. Okay, then you can always find some choice of coordinate transformations such that this quantity on the right hand side, del x prime alpha prime by del x alpha, del x beta by del x prime beta prime, plus del x gamma by del x prime gamma prime times gamma, plus this piece. Okay, this entire piece on the right hand side would add up to 0. Okay, fine. So gamma alpha beta gamma is not 0, but under coordinate transformation, gamma alpha prime beta prime gamma prime can be set to 0. Okay, now notice a distinction between what happens to gamma versus what happens to tensors. If a tensor is non-zero in one coordinate system, it is non-zero in all other coordinate systems related by GCT. Okay, whereas that is not true here. And it is just as well, because then you can simplify your geodesic equation by appropriately choosing a nice frame in which gamma alpha prime beta prime gamma prime is 0, and you can solve this equation in a very simple form, and then do a inverse coordinate transformation to obtain the solution in whatever frame in which you wanted the solution to be. Okay. So it is not that only tensors are very useful objects, even non-tensors are very useful object, and we will, throughout this course, we will kind of conveniently use non-tensorial property of gamma as well as tensorial properties of various tensors that we will be dealing with. Okay, I did not name this object, but gamma alpha beta gamma is an object which is called Riemann-Christoffel connection. Okay, that is just a name, but that's what it is called. So I think I'll stop at this point. We will kind of take up from here. Maybe there's an exercise that you may want to kind of do, that is that, remember, we had defined gamma initially to be this. Okay, del x prime alpha prime by del x alpha, del 2x alpha by del x prime beta prime, del x prime gamma prime. So what I'm trying to do is that instead of using x alpha coordinate, just use some other coordinates, say xi mu, okay, which are coordinates of some frame. Okay, and if you define your gamma exactly the way we had defined initially to be that object, do a coordinate transformation, say x prime alpha prime to x alpha now. Okay, check that this object transforms in this fashion. Okay, that is the transformation that we just saw. Okay, well, we didn't see, we just claimed that if gamma transforms this way, then the equation will be form invariant. Okay, now we want to do a check that the way initial gamma was defined, where we basically started with a Minkowski space free particle and did arbitrary coordinate transformation, we landed up with this object, we defined that to be gamma. What we'll do is that we'll do this exercise and check that this gamma actually does transform in a form that we have postulated here. Okay, so it is not like we are doing some random postulate, but the first example that we had used for defining geodesic equation actually does satisfy this property. Okay, so I think I'll stop at this point. Any questions?
Sir, so the second term in the transformation of gamma,
Yeah.
is there because we are going from one equivalence class of inertial frames to another equivalence class of inertial frame?
Yeah.
Is that right?
In a way, yes. Yeah, I mean, this is the object which relates to frames which are accelerated with respect to each other. So in that sense, yes, that is how the relation is.
Okay. Yeah.
Sir,
Yes.
when talking about inertial frames, you said uh, rotating frames are also inertial.
No. I didn't say that. I just said that like the frame rotated with respect to the other one would also be inertial. Okay, but not the rotating frame. I said the Lorentz.
Okay.
That
It's
means
just the
you may have one frame pointing in one direction, another frame may be like 35-degree rotated. Okay.
okay.
That frame is also inertial as long as it is related by Lorentz boost. Okay.
That is fine.
Not the rotating frame. I didn't say that. Any other question?